Hey guys, what's up? Kelvin here. Welcome back to a new YouTube video. It's been a while since I've uploaded my last YouTube video, right? It's been like a month or something. Yeah. Sorry about that. Life got in the way of me making videos, and, well, when life gets in the way of your projects, you know it's annoying. But we're back today, and this is going to be the start of something called Short Session Sundays, where I make a super short video, well, relatively short compared to my other videos, probably about 10 minutes long-ish, about one specific topic. So in this case, this is going to be a CCNA level overview on something called route summarization. This is just going to be a subnetting part of it. There's actually going to be no configuration today, despite the configuration that you see here. It's just for me to show something. But this is going to be the purpose of route summarization and the actual subnetting part of it. The CCNP video, I'm actually doing two videos today. So the CCNP video that comes after this will cover the configuration of route summarization for EIGRP and OSPF. Maybe even BGP if I feel like it. But for now, we're just going to be doing the CCNA part of route summarization, which is what is route summarization and how do we do the subnetting. So what is route summarization and why would we want to use it? Well, let's go ahead and look at this example topology sub over here. Super nice drawing, right? I've got two routers here, have a link between them. Presumably, I don't have the configuration listed here, but presumably these two have the necessary configuration on their interfaces to become fully OSPF adjacent. And so you can see here, I've got a couple subnets listed here, and I've got a couple loopback interfaces. So this is just to represent R1 originating a route that's destined for itself. So let's say I've got this loopback interface here. I've got the IP address configured of 10.10.0.0.255.255.255.20. This IP OSPF network point-to-point is an OSPF thing, just to make sure that it actually advertises the real subnet mask of the loopback interface as opposed to what it would do regularly if I didn't have this command, because if I didn't have this command, it would actually advertise this route as 10.10.0/1/32 instead of what I wanted to be advertised as, which is 10.10.0.0/22. So it's going to advertise as a host route, hence why I have that point-to-point thing there. And then IP OSPF 1 area 0 is just to go ahead and originate a route for the subnet of that interface into OSPF. And we've got similar configurations on all of these loopback interfaces, difference being the differing IP addresses. Anyway, when R2 gets these routes, because presumably R1's going to package these into LSAs and send them off to R2, presumably these are intra-area routes, they'll be packaged into type 1 LSAs, but I'm getting beside myself. When R2 gets these routes, what is it going to think? It's going to put it into the routing table. When you do a show IP route, it's going to have, let's say, 10.10.0.0/22 from OSPF via, let's say, this interface, this gigabit Ethernet 01. Point is, it's going to destine any packets that are going to that subnet. It's going to send them out gigabit Ethernet 01 over to R1 here. If I've got a packet somewhere on this side of R2 that comes in and it wants to go to 10.10.0.1, it's going to go out this gigabit Ethernet 01 interface to R1. Now, here's the problem with that. This is just 5 routes, right? And it's fine, right? The CEF can definitely handle 5 routes in the routing table. That's no problem. What if this were not 5 routes, but 1,000 routes, 2,000 routes that were all destined for R1? That's a tiny bit wasteful of R2's routing table space, especially if these are consecutive subnets. So if you notice the subnet list over here, I've actually included the ranges. You can see 10.10.0.0, 10.10.3.255, 10.10.4.0, 10.10.5.255. You can notice all of these are consecutive subnets, and we've got 5 routes for them. It's a tiny bit wasteful to have those 5 routes listed in R2's routing table when all of them go to the exact same place. So, what do we do in this case to optimize the memory usage of the routing table? Well, what we can do, if my doc can get out of the way, please. What we can do is something called route summarization. And with summarization, what we're doing is we're kind of making an umbrella subnet. So let's go ahead and make an umbrella subnet here. So we've got the full range of all of these subnets is 10.10.00 to 10.10.7.255. That's the full range of all of these subnets, right? So we need to find a subnet that will include all of these. Well, let's go ahead and experiment with subnet masks. So you can use your own method. Actually, I would advise you pause this video right here and try to find the subnet that includes all of the addresses in this range, right? But I'm going to use a quicker method here just to go ahead and reduce the length for this video, but I would advise you pause this video and try to work through this yourself and then resume the video when you're ready to see the answer. Anyway, so we see that there's 10.10. That's the same between the beginning and end of this range. So we know that we can safely say that this mask begins with 255.255. So it's at least a /16, at least. We've got the first 2 octets of our subnet mask done. Now we need to find the last 2 octets. So basically we know that the last octet is 0. And the reason I know that is because, well, you can only have a consecutive set of 1s and then 0s in the subnet mask. I won't ever have a subnet mask that looks like this, 0.255, right? I won't ever have a subnet mask that looks like this. So in order for this last octet to be anything but 0, this has to be 255. Because, again, it's a consecutive set of 1s and 0s. For this to be anything less than 0, right, or more than 0, I'm sorry. For this to be anything more than 0, there would have to be at least 1, 1. That's a funny thing to say, 1, 1. 1, 1 in front of the octet for it to make 128, and 2 1s to make 192, and etc, etc, etc. So, in order for that to happen, this would have to be 255, meaning that between the beginning and end of this range, this third octet would have to stay the same in IP address. And it doesn't. It goes from 0 to 7. So therefore, we can deduce that this third octet is not 255 for sure, and therefore, this has to be 0. Because if this were anything but 0, there would be a 1, which means that there would be zeros in front of a 1 here, which means that we'd be breaking the rules of our subnet masking. So that's a quick way to deduce that this last octet is 0. Now, that just leaves our third octet. So what we know about a third octet in this case is that at the beginning of the range, our third octet is 0, 0, 0. And at the end of our range, the third octet is a 7. So we have 0 to 7 as values for the third octet that we need to be included in our sort of umbrella, our overarching subnet. Well, how many items are in an array that consists of 0 to 7? Well, if you actually count, you can count your fingers if you want, from 0 to 7, you'll know that we have 8 items in that array because we're counting 0. So we need a subnet mask that can accommodate 8 different third octet values. Well, let's go ahead and do our powers of 2. We have 2 to the power of 1, which is 2, 2 to the power of 2, which is 4, and then 2 to the power of 3, which is 8, right? Thank you, OneNote, for helpfully filling that in, right? We've got 2 to the 3 equals 8. So we need 3 bits to be able to play with in order to make our 0 to 7 in our third octet. Well, we need 3 bits to play with, so we need 3 zeros, because the 1s mean that it has to stay the same, right? 255, means that this 10, has to stay the same from the beginning of the range to the end of the range. In this case, we do see that 10 stays consistent. So our 1s, we can't manipulate. But if we have zeros, then that means that those bits in the IP address can be manipulated with, and it will stay in the same subnet. So in this case, we need 3 zeros, and the rest of them are 1s. Well, remember what I said earlier about consecutive 1s and then consecutive zeros? Well, that means that it would be 5 1s, because an octet is 8 bits. So we have 1, 1, 1, 1, 1 as 5 1s, and then we have 3 zeros. So 5 1s is 128 plus 64 plus 32 plus 16 plus 8. This adds up to 248. Thank you, OneNote, for helping filling that in. And this is our subnet mask, 248.0, which is a /21. Right? And you can check, and you know that that's true because we have these 3 bits here that are zeros, and if these were ones, then this would be a /24, 255, 255, 255, 0. So that's how we know that this is a /21. So the final subnet is 10.10.00/21, and this has a range of 10.10.00 to 10.10.7.255. This one subnet range can comprise this entire block of IP addresses. So, while I'm not actually going to configure route summarization in this video, this is basically it. You can see here we've made a summary subnet that is 10.10.00/21 that has this range 10.10.00 to 10.10.7.255, and if we were to configure route summarization, this is the subnet that we would use. So that wraps up for this video. In the next video, we're going to go ahead and look at the CCNP level of this content, that is to say, actually configuring route summarization, putting these into OSPF. I'm going to fire up the viral lab back here. Yes, I did get viral. Yes, I still have JNS3, but that's something we'll go into in the next video. But yeah, so again, in the next video, we're going to go into configuring route summarization in EIGRP, OSPF, and BGP. And we're going to go ahead and look at how we can use the subnet that we deduced in this video to advertise one summary route from R1 to R2, and therefore optimize the routing table usage on R2. Anyway, have fun guys, see you in the next video.